Okay, so let's continue on here with the handout we were doing the other day. How far did we get? Did we get through the second part or just the first part? Just the first part. Okay. So the second part says set up the equations for calculating the volume by rotating the area around the x-axis using the shell method. So to do the shell method around the x-axis, you're going to put the rectangle horizontal because you want to create these little empty cans. So that's the first thing you do, is you're going to draw your rectangle. Once you draw the rectangle, the rest of it shouldn't be too hard. So I'm going to let you. So there's your shell. You're rotating around the x-axis. So if you, what's one thing we can say about how does the orientation of the rectangle tell us about whether we integrate with respect to x or with respect to y? So, Elias, do you think we integrate with respect to x or y? Why is that?
Because it's a horizontal.
Yeah, so you'd end up stacking them in the y direction. So because of the orientation of the rectangle, we know everything has to be in terms of y. The limits have to be in terms of y. The equations have to be in terms of y. And the whole equation has to be in terms of y. So you're not going to have to memorize the formula. So you'd go, oh, let's see what formula I need to use for a shell method around the x-axis. And what you'd find out, this equation is 2 pi times the integral from c to d of p of y times h of y dy. So we just have to figure out what the limits are and what the equations are, p of y and h of y. So let me see who I'm going to ask here. So Daniel, so what is p of y? Y, yeah, because p of y, it's always y when you're rotating around the axis. Now p of y would be something different if you rotate around another horizontal axis. So p of y is y. Now we can't do h of y yet because we have to solve the equations that define the boundary. So what equations do define, what curves define the boundary? Well, the boundary is defined by the ends of the rectangle. So on this case, we have the line. What is the equation for that line right there? Is it x equals 0 or y equals 0? Yeah, it's x equals 0. It's the y-axis, but it's x equals 0. So, we have to have the functions in terms of x. So that it just has to be x equals something. So this equation is already in the right form. So one of the equations that make up h of y is just x equals 0. And then we need another equation, x equals something else. So what is that curve? Well, it's this curve. It's in terms of y here, so we have to solve this for x. So go ahead and solve y equals x squared plus 4 for x. And you'll get a plus or minus square root. The question is this the plus square root or is the minus square root? So we'll plus or minus the square root of something. So let's see, Savannah. Yep. So it's what did you say, plus or minus? Not that I couldn't remember what you said. Was it plus the square root or minus the square root? What you think you're going to say plus? Good job. So it's plus the square root. It is because it's the x value is positive, so it has to be because the x value is positive, it has to be the positive square root. The negative square root would be this way, be on the negative side of. It's kind of hard because we're used to looking at everything the other way around. Okay, so that's the equations. So those are the two equations, and so h of y is just going to be the difference between those two, and you always subtract the one that's more negative from the one that's more positive. So relative to x, this one's more positive and that one's more negative. So you're going to subtract this from that, which in this case is just the second. So in this case, h of x, or h of y is equal to the square root of y minus 4 minus 0, which is just the square root of y minus 4. Okay, so that's h of y. So the only things we need to find out now are the limits. And so you look in the y direction, what values of y define where I start my integration and where I end my integration. So Zane, what do you think the limits are? They're kind of small numbers, but this is 2, 4, 6, 8, 10, 12, 4 and 13, yep. So A, C and D are 4 and 13. I don't know why I had two extras. So the equation is the integral of 2 pi times the integral from 4 to 13 of p of y, which is y, times h of y, which is the square root of y minus 4 times dy. Now the question may be, this is not a simple polynomial integration. Well, I guess it could be. Yeah, it is actually. No, it's not. Yeah. If it was just y times the square root of y, then you can multiply those together and get, you could get y to the 3 halves, and you could integrate that. But in this case, it's not the same. So does anybody remember how we might integrate that expression? Yes. Oh, sorry. I saw Daniel, but go ahead. But you can answer it. So what would you let u be? And what do I do about this guy here? Right, yeah. So this is that second type of u substitution that we talked about. So you would still use u as being the y minus 4, but then what you would do is you would solve for y is equal to u plus 4 by solving for y, and dy would be equal to du. So then you'd have to redefine the limits in terms of u. So you'd say when y equals 4, u equals 0, because you'd have 4 minus 4, and you'd say when y equals 13, u is equal to 13 minus 4, which is 9. So the integral would become 2 pi times the integral from 0 to 9 of, for y we put in u plus 4, and for the square root of y minus 4 we put in u, and then you have du. And then you'd multiply it out, so you'd get u to the 3 halves plus 4 times u to the 1 half, and then you'd integrate it, and then you'd use the u limits. You wouldn't, because we're doing a definite integral, you wouldn't substitute back in. All we care about is a number. We don't care about putting it back in terms of x. Okay, so we're not going to do that, but that's how you would do that integral. Okay, so moving on to the next one. The next one says, set up the equations for calculating the volume by rotating the area around the y-axis using the disk method. And so one question may be is, Why don't I have to use the washer method? We've been using the washer method. Well, I guess the first question is, how would you orient your rectangle to do the disk method? And then maybe we'll ask the second question. So here's your picture. So let me ask somebody, if I want to make a disk around the y-axis, Lexi, or am I going to make a horizontal rectangle or a vertical rectangle? Yes. Yep. So it's horizontal, and so it's going to look like this, because if I had it the other orientation this way, I'd make a shell, but by rotating this or orienting it this way, it becomes a disk. So that kind of answers the question, because the reason it's a disk is because this boundary is the y-axis, whereas when we did the previous problem here, it was a washer, because the interior surface, the interior is not the x-axis. So that's why we use the disk method. So once you know it's the disk method around a vertical axis, you go to your cheat sheet and you say, oh, what's the equation? So the equation would be the volume is equal to pi times the integral from c to d of r of y squared dy. So we only need to know three things here. We need to know c, d, and r of y. And we can actually use the previous problem that we just did. Remember, whether you're doing the disk method around the y-axis or the shell method around the x-axis, because of the orientation of the rectangle, you're going to be integrating with respect to y. That's why the equation is y. So instead of these two surfaces defining the height of the shell, those two surfaces define the radiuses. So the same equation that we used here for this equation, when we solve for x, we can use for the radius, except we're going to square it this time. And the limits that we came up with in the previous problem also apply. So if you do one, not one exactly one, but the same orientation but around a different axis, all the information that you use to develop the integral is the same. So if we go back to our previous problem, we found out that this red curve, this curve here was x equals the square root of y minus 4. So that's r of y. So we have the square root of y minus 4, and the limits are from 4 to 13. So then you get the volume is equal to pi times the integral from 4 to 13 of the square root of y minus 4 quantity squared dy. And now, again, I'm not going to do the integral, but you can see that integral is a piece of cake, because you're going to have, when you square the square root, you just have y minus 4. So that's just a simple polynomial integration. You don't have to change variables or anything. Okay, so now going to the next one, we can kind of refer back to the first problem that we did. It says set the equations for calculating the volume by rotating the area around the y-axis using the shell method. So what I'm going to do is see if you can do that. Okay, I'll tell you the equation, but see if you can figure out, either referring back to what we did earlier or just by thinking about it. Let me make a copy of this. I'm not going to tell you which way to orient the rectangle, but if you look at the equation for the volume using the shell method around the around the y-axis, it's 2 pi times the integral from a to b of p of x times h of x times dx. So just the equation should tell you which way you have to orient the rectangle. Okay, so I'll just chill out for a minute here instead. You can talk to your neighbors if you want to see if you. Yeah, I'm trying to decide what I'm playing for you guys on my trumpet, because the second trumpet part's not always the most interesting part. So you're like, what? It's kind of like playing the euphonium, probably, right? Do you ever get any melody? No. That's one thing about playing in our group, is that every instrument gets the melody at some point. So even the second trumpet. I'm the only you got the horns, you got the trombones, you got the tuba, you got the first trumpet and the second trumpet. So I'm the subordinate. That's okay. Actually, why don't you go ahead and integrate this one. I don't think it's going to be that difficult. So yes.
This is definitely a 4.
Oh, is it? Okay.
Yeah, you can see I get kind of lazy doing 4s.
Yeah, it always looks like an 8 to me. That's why.
Yeah, that's
Okay.
that's just my lazy.
That's your lazy. Okay, okay, that's fine. I'll just keep this. But by the way, I've got to leave it on the dot at 9, so I'm going to give you your test and let you just walk it over to the library for physics.
Okay.
Okay. I'm not giving you any more credit. No, just kidding.
I have a question about this.
Yeah.
I'm having trouble figuring out with each method which line to have above the other.
Yeah.
Subtract from. It's like,
Yeah, I mean, in this case, you've got, this is the top, you just see where the top part of the rectangle is, and this is the one that's more positive in the y direction. Because you always have to have this difference to be positive, because you're getting a positive area, of positive volume, so the difference always has to be a positive. And therefore, you always take the one that's more this direction, the top line, and then you subtract the bottom line.
So like with the shell method, you have to do that in respect to the x-axis rather than the y, even when you're moving it around the y.
Yes.
Okay.
Yes. Yeah, because you still need that difference to be positive. H of y still has to be positive, or h of x in this case. Yeah, h of x has to be positive. So whether it's you're going around the y-axis, that difference still has to be positive to get. It's basically the length of the can, and if you did it the other way around, you'd have a negative length of a can, which wouldn't work out.
For this, I'm just double checking. H of x would be like this minus 0 because of.
Well, this is the bottom. The top is this line.
Okay.
So actually this is the wrong orientation.
Yeah,
It would be 13 minus x squared plus 4. Yeah. Mm-hmm. So those are the, so remember we're doing the shell method. So the radius of the shell is this p of x, which just turns out to be x. And then the height, or the length, the extent of the hollow shell is going to be this. And so you take the difference from this y value down to this y value. So it's 13. This stays constant, whereas the bottom varies. So you subtract x squared minus 4. And if you evaluated 13 minus x squared plus 4 at any place between 0 and 3, it would be a positive number. That h of y or h of x always has to be a positive number. And you can normally tell it by how the rectangle is, what the extent of the rectangle is. Whatever's at the top of the rectangle is your thing you have first, and then the second thing you subtract is the bottom part of the rectangle. Even though it looks like 13 minus x squared might give you a negative number, it doesn't under those circumstances. So Xavier, I'm going to fix your, I don't have a pen, but I'm going to fix your grade. So I'm going to disconnect his for a second while so you don't see everybody's grades. Okay. Yeah. Yes. See that's very instructive. I did that on purpose. No, I didn't. Yeah, thanks sure you're paying attention. No, it shows you how, I harp on parentheses, right? And I didn't use it there. And I fell for the same trick. So I left that parenthesis off. I'm thinking I was lazy. And so when I went back after fixing Xavier's test, I forgot it was supposed to be negative in front of both of them. And then so even somebody who's been doing this forever falls into the same trap. So make sure you leave your parentheses on there. Okay, so let's see what we got here. 2 pi times 9x squared. Is that the right answer? Okay. So, yeah, we just, I still didn't put the parentheses in. Well, I guess that's okay. Let me just, that was the same thing. So once you do that correctly, So you add 1 to the exponent, divide by the new exponent. Same here. Plug in 3, 0. I didn't even put it up there because it's 0. The lower limit gives you 0 because it's a polynomial. And you just simplify it. Okay. So the next, the problem, somewhere here. There we go. So there's the figure. It says, would a vertical rectangle or a horizontal rectangle work best in this situation? The function is y equals 10 over x squared. So the question, you could solve this problem using whether you were doing around the x-axis, the y-axis, the shell method, or the washer method or the disk method, whichever one applies. But one of the orientations would be much easier. So you could put in a vertical rectangle and think about, in terms of what function would define the upper part of the difference between the two, or you could do a horizontal rectangle and think of how that would look, and how the upper curve relative to a horizontal rectangle, upper or not really upper, but greater in the magnitude direction. So think about it. I'll give you 30 seconds to make a decision. You have to vote yes or one way or the other, horizontal or vertical. It's worth 10 points extra credit on. No, just kidding. Not to put any pressure on you guys. Okay. Okay, so here's the vote. So how many people vote for a vertical rectangle? How many people vote for a horizontal rectangle? Why did you vote? Hannah, you voted because everybody else voted that way. So why do you think they voted vertical? What's that? They know what they're doing. Does that mean you don't know what you're doing? Is it? Okay. So for you guys, let's see. Great. Why did you think a vertical? Well, let me just draw one. I'll ask you the questions here. So here's a vertical rectangle. So we're assuming this area is this part right here, okay? So it's defined by the x-axis, this vertical line, and this curve. So does the inner radius change at all during the integration? No. Does the upper line change during the integration? Is it always this curve? Yeah, until we get to here. Okay. Now, if I rotated the rectangle horizontally instead, so let's get rid of this thing. So does this less y value part of the rectangle stay the same during the entire integration? Yes. How about the top curve? No, because during this part, the upper curve is here, and then the upper curve is this little line there. So if you did a horizontal rectangle, you'd have to have two integrals. You'd have to integrate from y equals 0 to y equals whatever this value is. And then you'd have to integrate from y equals this value up to there. Now, it turns out that this number is not a whole number, it's some fraction. So not only do you have to integrate twice, but you'd have to integrate, you can see it's some number less than 1, because here's 2, there's 1, so it's got to be some fraction. So you'd have 2 integrals instead of 1 integral. You'd have the limits, if you had a vertical rectangle, then the limits go from 1 to 4. Here they go from 1 to, like I said, whatever that value y is. Now you get the same answer whether you do it either way, but in this case it makes a lot more sense to do a vertical rectangle than a horizontal rectangle for those reasons. So let's look at this same question on this one. Would it make more sense to have a horizontal rectangle or a vertical rectangle for whatever calculations you do? So we'll take a vote on that one in a second. So you can draw the rectangles in there and think about, can I make it so that I only have to do one integral? So we were talking about church yesterday. Was it in this class or another class? It must have been another class. So, it snowed on Sunday. And I play in the praise group at the early service. And we went out and get in the car. And we live up on a hill. Seth knows where we live. So I get up there. I'm thinking, this is stupid. Why am I doing this? So we started to go down the hill, put on my brakes, the anti-lock brakes going, which is not good, going down a hill, okay? You don't know how much you're going to... So we ended up driving down the bottom of the hill and just continuing, come back around, looped back up, went in the driveway. And so at the early service, there were 3 people that showed up. The minister, the other person that sings in the praise group, and the other person that sings in the praise group. No people in the congregation. And then I saw Mark Mason, the Mason. He said there were 11 people at the 11 o'clock church, so including the minister, the choir director, the organist. So that makes, and the Masons, which is about 8 people. That must have been, that was, there are a lot of them. So we boycotted. So it's crazy. Okay, so let's, so how many people vote for a vertical or rectangle? How many people vote for a horizontal rectangle? Okay. So it looks like the horizontal rectangle wins. So Evan, why horizontal one?
It would be easier to just take the difference of the 2 functions.
Right. Yeah. So if we draw the, well, let's just do the vertical first. Again, if you have a vertical rectangle, you're going to have 2 integrals. You're going to integrate from here, x equals here, to x equals there. And again, I don't know if this is, it looks like it actually is a whole number, but maybe not, because it's a square. Well, yeah, it is probably. And then you'd have to have a second integral where this is now the top function. Whereas if you do it horizontally, then no matter where you are in this interval, the top curve, the blue curve, remains the same, and the red curve remains the same. So that's why a horizontal one would work. So I'm just going to go through these quickly so we can finish up this handout. Same thing's true here. You'd use a vertical rectangle, because if I use the horizontal rectangle, then you'd have to integrate. A horizontal rectangle would require you to have 2 integrals, whereas a vertical rectangle would just have 1 integral. Okay, and then the one previous to that. So I think the questions just say, would a vertical or what specific questions do they ask here? So this one says, would a vertical or horizontal rectangle be better to use? Well, the answer is a vertical rectangle. What would be the integral needed to find the volume due to the area rotated around the x-axis? And because we're rotating around the x-axis with a rectangle oriented this way, what method is that? Is it a shell, a disc, or a washer? Yep, it's a washer. So because of that, we could look on our cheat sheet and say, oh yeah, the washer method for a, whoops. Somehow, what happened here? I lost my, oh, there we go. So I decided to do a vertical rectangle, and because I'm rotating around the x-axis, then I know it's a washer, and the equation for the washer method with a horizontal axis of rotation says the volume is equal to pi times the integral from a to b of r of x squared minus small r of x squared dx. So that tells me, okay, I need to know what my x limits of integration are, which are going to be 1 and something between 3 and 3.5. It's not actually, you'd actually have to solve for that point of intersection. Actually, what we'll do is we'll take a little more time. We're not going to hand this in today. We'll just finish up the last little bit on tomorrow. It's Friday. Okay. So I'm running over to Rockbridge today, so we'll finish a few minutes early. And I do have a couple of homeworks to hand out here that do have checks on them. So let me, Xavier, here's your homework. And then Kelly. There you go.